right, here we go. So now my question is this. Do you remember this funny little thing that was like we looked at a change in momentum, and that change in momentum was like force times change in time, and we called that impulse. Do you remember that? And there was like this fancy J looking symbol that you see. It's like a script J, and that means change in momentum. It is the impulse, which is F delta T. And we could even graph force versus time. And let's say the force was constant. We'll keep a boring force there. And if you had this graph of force versus time, what did the area under the graph give you? But if it was distance, it would be work. That's where it gets tricky. So it's the impulse or the change in momentum is the area under the graph. So, keeping with my analogy, if I had a change in angular momentum, it would be torque times the change in time. And if I graphed torque versus time, what would the area under the graph be? Not just the angular momentum, but the change in the angular momentum. It's little words like that that have a big meaning when it comes to physics, and I want to make sure that you guys are careful with that. Okay, so let's look at an example where we take a wheel with a mass of, so we have a mass of 2 kilograms, radius of 25 centimeters, spinning at a rate of 10 radians per second. How much torque is needed to stop the wheel in 5 seconds? So we're going to stop it. It's spinning. It's a wheel. It's like a bicycle wheel. We'll ignore the spokes. So what could we model a bicycle wheel as? What shape? A hoop. Very good. And what's the moment of inertia of a hoop? Yeah. The mass times r squared. Okay. And does our angular momentum increase, decrease, or stay the same? We go from spinning at 10 to stopping. Yeah, it decreases. So there's a change in angular momentum. And the change in angular momentum is due to a net torque acting on it for a particular amount of time. So I'm looking for the torque. How could I find the torque? Can you find the change in angular momentum? So let's see. We'll have our final angular momentum minus our initial angular momentum is the torque times the change in time. Now let's see. So angular momentum is I times omega. So this final one would be I times omega. And if we're going to stop, what's the final angular speed? So what's the final angular momentum? 0 minus, okay, so I for the hoop would be mr squared times omega, initial, torque delta t. Okay, so then 0 minus, the mass of the wheel was 2 kilograms, I think. Our radius is 0.25 squared. And then the angular speed was 10. Torque is unknown, but our time is 5 seconds. So, how much torque has to be applied to this wheel? All right, I got a negative 0.25 Newton meters. Why negative? But why does the negative make sense? And it's going to slow it down. So the torque has to oppose the motion. That's right. Now, what does a negative torque mean? So if this wheel is spinning clockwise, you take your right hand and you wrap your fingers in the direction of the spinning, and your thumb would point into the page. Okay. Now, another analogy that we can look at, do you remember when we had collisions occur and things stuck together? We had a conservation of linear momentum. So that was like the sum of all the initial momentum was equal to the sum of all the final momentum. And there was an asterisk to that, a footnote, and that was if no external forces act on the bodies. So that means that the only force that can be in the system is the action-reaction force between the two pairs that are colliding. So that's the Newton's third law business. We can only have the action-reaction forces between the two. Okay, so similarly, I can have a conservation of angular momentum. The initial angular momentum would be equal to the sum of the final angular momentum. If, what would the asterisk be now? If no external, not forces, but so no external torques act on the system, then our angular momentum would also be conserved. So when I see you again, we will collide things that are spinning. Like, oh my goodness.